I'm your host. This is our monthly tech meetup. And the idea being we're in the North End, so it's a way to get people together without having to fight the downtown traffic if you don't happen to work downtown. Now nobody works downtown and there is no commuting, and we're just keep going anyway because it's kind of fun to get all these experts in talking about different things. So today our presentation will be by Jeff Hasboun. Presumably I pronounced it right. In fact, I should ask you, Jeff, is it Hasboun, Bon?
It has Boone, like Daniel Boone.
Hasboun, I wouldn't have guessed. Okay. Yeah. He'll be talking about the nanograv experiment. He has quite the background, I've learned, with a degree in biology and full-time river raft guide, and dabbled in chemistry and all. And now he's ending up in hardcore physics. And I don't know if it gets much more hardcore than this. So during the presentation, I will be monitoring the chat box. So if you have questions at any time, put them into the chat box. And whenever there's an appropriate break, I'll have Jeff answer the questions. He'll also be pausing for questions while we continue. And there'll be plenty of time for questions at the end. So without further ado, I'm going to turn it over to Jeff Hasboun.
Awesome. Thank you so much for the introduction, Ken. I'm going to, it says that I'm going to share my screen if that's okay.
Oh yeah, I need to let you do that. Hang on. Let's see. All participants. Okay. You should be good. You should be able to do that.
Yep. Great. So I have a number of slides here, and with a group this size, I'm happy to let the conversation sort of go where it will, and we can get through them, or we can get through 6 of them and have a great conversation. So it's whatever you all want to do. And I'm giving, like I said, or like Ken said, there'll be opportunities to stop and answer questions in the middle. So I am a postdoc, senior postdoctoral fellow at University of Washington, Bothell. I work in the Key research group in Bothell. So that's Joey Key, who spoke to you all a couple of years ago. And I work for a collaboration called NanoGrav, which is the North American Nanohertz Observatory for Gravitational Waves. And we're a physics frontier center. There are 10 physics frontier centers that are funded by the NSF. So just I have to put this number on everything to let you all know that your tax dollars are helping to pay for this amazing, fun research that I get to do. And I am going to just do an introduction about gravitational waves, just to make sure that we're all on the same page on this topic, and introduce sort of all of the ways that we can detect gravitational waves. Then I'll get into pulsar timing arrays in particular, which is the work that I am most passionate about. So for a long time, the only way that we really observed the cosmos was using light. So sort of everything we know about the universe until a few years ago was from the photons that came to us from everywhere in the universe. And across the spectrum, radio, whether it was in radio, X-ray, optical, obviously, famously Galileo and the optical, and we use photons as our messengers, right? It's that light traveling from very far away that gives us all of this information that we need, with a myriad number of instruments. So there's some of these this is the VLA in New Mexico. This is the Hubble Space Telescope. This is Planck, which was measuring the cosmic microwave background. So that's in the sort of microwave. This is Fermi, which is measuring gamma rays. So sort of across the spectrum. And this is a much more modern version of what Galileo was pointing at Jupiter to look for the moons. And so there are we can see things that give off light or interact with light, right? The 2 ways that you see things in the universe outside of the Earth are either the thing that you're looking at is giving off light, or it's somehow interacting with light, whether that's a reflection of light, say for the moon, or there's a star behind some cloud and the light that's coming from the star interacts with the dust or something else, and it tells you something about the interim material. Those are really the ways that we see things, is this interaction with light. And this is sort of a short history of that. So we've kind of got the wavelengths here on the right, and some sort of mile markers along the way. Obviously, Galileo with optical astronomy, Carl Jansky with radio astronomy, and various other projects that were the first of their kind to sort of open up a new part of this window, of this EM window. And there is also particle physics. So cosmic ray astronomy is really these high energy particles. They don't often, not very many of them, make it into the atmosphere. So we started to see these when we sent balloons up into the higher atmosphere. Higher energy ones can make it to the ground, and we see those. We've also started being able to do neutrino astronomy. So Davis and Bacall, the experiment where they basically put this detergent in these cylinders and saw how neutrinos interact with either the heavy water or whatever other molecules they had. This has been ongoing, and we measure these neutrinos. We can see neutrinos from supernovae, things like that. So we do have other messengers besides photons. The vast majority of what we see is through that. And then since 2016, really 2015 is when the detection was made, LIGO has opened this completely new window using gravitational wave astronomy to be able to see things. And so the idea of gravitational wave astronomy is that gravity itself is the messenger, just like electromagnetism and photons and light are the messenger for regular telescopes. So you don't look with light, you look with gravity. And gravitational waves are awesome because they're complementary to photons, right? Photons are made by atoms. We see things, again, that interact with atoms because the photons interact with the atoms. Gravitational waves are made by either the dynamic motion of matter or through more exotic means. I'll talk about some of those maybe a little bit later, but anything that's really massive or very, very dense, when it interacts energetically, can give off gravitational waves. So it's these really big, dense things. And a lot of what we're going to talk about actually is the stellar background. So the remnants of stars that don't really give off that much light, white dwarfs, things like that. Go ahead. Is there a question? Okay. So we call this the stellar graveyard, right? So black holes, stellar mass black holes, big black holes, neutron stars, things like that don't give off a lot of light. So all of this story starts with general relativity, and these are just the key points of why this young patent clerk decided that he had to figure out a new theory for gravity, which had worked fine for 300 years. Basically, he couldn't reconcile Newtonian gravity with his new theory of special relativity, right? Special relativity says nothing could travel faster than light. Seemingly, the equations of Newtonian gravity say that you instantaneously know what the new gravity is. If you change a mass and you're, out at Jupiter, you instantaneously see that the gravitational field has changed. And so that speed of light wasn't built in. And that's actually what started him down this path of trying to understand, of generalizing his special theory. It wasn't called the special theory of relativity until he actually came up with the general theory of relativity. And it all leads to this idea of the curvature of space-time as gravity. Okay, so the idea, this picture that people see, right, is that there's some massive object in the center. This is like, imagine this is an elastic sheet, and there's this big mass at the center. And we're going to sort of forget about what that mass is for a second and just think about how other particles that we always call test particles interact with that massive object. And basically, you can imagine a marble, right, with some speed you've given it and there's no friction. It's just going around in a circular orbit, or you get an elliptical orbit sending something down in like this without any rolling friction, right? This little marble would just keep rolling on that same path over and over again. Of course, there's unbound orbits as well. This elastic sheet analogy is okay, but it really is just an analogy, right? So I love, this is an XKCD comic that I really love. Really that analogy breaks down, and space-time is like this set of equations for which an analogy is just an approximation. The sheet, really you're bending space-time in 4 dimensions, and this picture is really just showing 3 of them, the 3 space-like dimensions, and there's this extra time one too. And the things like time dilation, right, that comes from this bending of the time coordinate. So it really does have to do with the math. And here's the Einstein equation here on the upper right. There, I can show you more more complicated versions of it. But basically, there's some sort of geometry that is based here that says that space-time curvature is equal to some particular expression for the matter and energy content of the universe. And this matter tells the space-time how to curve, okay? And then this equation doesn't actually tell you how it moves. There's a different equation called the geodesic equations, which the geodesic equations just say, this is the shortest distance in this new curved space-time, and that's how things are gonna move. They're gonna move by the shortest distance. That's just the same as Fermat's theorem, right? That says that light is going to go along the shortest path. So space-time then tells the matter how to move. And this is this famous example, right, where there could be a star behind the sun, and the light ray, and in particular, this is really important because in normal in Newtonian gravity, masses interact with masses, but light has no mass and doesn't interact with things via gravity. But light in general relativity does get curved. It moves along these, just like a skateboarder in a skate park. A gets bent and comes to the Earth this way, even though it should be behind the sun. And it looks like the light from that star is coming from this point B. And that was the sort of famous proof of Einstein's theory. And this was done in the late 19 teens with various expeditions to go look at solar eclipses, where you had some big dark disk covering most of the sun, so you could see the light coming from these stars that are just supposedly just behind the edge of the sun. Okay, so I'll stop there for the first time for questions. I kind of went through that introduction really quickly. If anybody has any questions they'd like to ask me, happy to answer them now. Give 3 more seconds of awkward silence, then I will continue on. So the awkwardness really draws out questions. Joey Key, my boss, is so good at that, especially on Zoom calls with her students in particular. I'm going to now shift to talking about gravitational waves, and this has been in the news a lot recently because of the discovery of gravitational waves. And almost 100 years after Einstein predicted the existence of gravitational waves, we detected them with LIGO. And gravitational waves are really just dynamic curvature. You know, I showed you this picture of this elastic sheet. Well, if you put 2 balls in an elastic sheet and you move them around each other, the elastic sheet is going to move up and down, up and down, up and down. And basically, that's the analogy to these gravitational waves. As these two two massive things, these are neutron stars here, or black holes, or something that's very, very dense, as they move, then you see these ripples in space-time. And this is predicted by the equations of general relativity. Einstein predicted this, and he never thought we would see this because it's a really small effect. And in fact, it took a long time to build the technology to be able to see this. So the question really becomes, how do we detect these gravitational waves? So if you want to detect a physical phenomenon, you have to ask yourself, what does it do to some physical system, right? So if you want to detect photons, you're usually having the photons kick something up in energy, like in a CCD camera, for instance, and that there's some photon gets detected, and you can actually count single photons and see something using that type of detector. Gravitational waves are a little bit different. And what we're thinking about here is that really what you have is that you're changing space-time, and in particular for gravitational waves, we're looking at changes in the space, the distance between objects. So you take 2 objects and you want to see how the distance between them changes. And gravitational waves have polarizations. And I have 3 pictures here, but there's only 2 polarizations. These 2 are the same plot, but there's a different animation hiding under them. And this one is a different one. This is called the cross polarization. So 1, 2, 3, 4. You have a circle of test masses. As a gravitational wave starts to move into the page or out of the page, you'll see it squash in one direction, then return back to the circular pattern, then it'll squash in another direction that's about 90 degrees to that. This is called the plus polarization, because as this thing moves, you'll see like a plus shape. And here's an animation of that. So this is the center of this thing. And so this is how the test masses around that move, but you can kind of see this plus shape materializing, and that's why we call this the plus polarization. On the right here is the cross polarization. Everything happens basically the same way, except things get squashed at 45 degrees to the plus polarization. And so you get test masses that move this way. These are two independent polarizations. These are the linear polarizations. You can get circular polarizations just like you have in light, but there are only two that are predicted by general relativity. And this is more of a, so this is just looking in the plane of motion. This one is what it looks like if you look past the plane of motion at that ring. And this is like peristalsis in action in your gut, right? I'll play it again here. That's what you expect things to look like in time as you move through. So this is the idea. Gravitational waves change this proper distance between these particles or masses, and we try and detect those. And this is what the waveforms look like of a particular kind. So these are LIGO waveforms. LIGO looks for these binary systems just as they're about to coalesce, right? So I'll talk a little bit more about the different kinds of signals you can get a little bit later, but it's just to show you that it's fairly easy even by ear. So it turns out that the LIGO signal, this is not sound, it is gravitational waves, but it's in the same frequency regime, around 20, 60, 100 hertz, that if you turn it into audio waves, you can hear things. And these are examples of a circular binary. This is two objects that are about the same mass orbiting each other, and this is the last moments just before they coalesce. So the signal builds, the frequency gets faster, and then right around here is when they coalesce. And once they coalesce, they ring down, and they become basically a cylindrically symmetric object, a spinning black hole, single spinning black hole if they're black holes, or single either very massive neutron star or black hole. And then this is what it looks like if the mass ratios are a little bit different. So you see a little bit of change in the waveform. This is a highly eccentric orbit where the two things are actually not very circular. And these are just the sound forms of this. This is the circular chirp. We call these chirps. You'll hear Y at the end of this. So the frequency is getting faster, the volume's getting larger because the amplitude is actually growing. And then you'll get to the chirp here in a second. It's only the last about half a second of that LIGO can see when they're actually looking for these gravitational waves, at least for black holes, which is their bread and butter signal. This bottom eccentric one, you can see there's actually many smaller oscillations in here. Then there's this sort of beat frequency that happens over the top of it, and that's what you hear mostly here in this eccentric waveform. Is that sort of beat frequency, and then it gets faster and eventually chirps. It actually becomes more circular as it coalesces.
Are you there?
Yeah.
Okay.
And were you able to hear that, Ken?
Sorry, I was muted. There was a long period of silence. It went beep, beep, beep. Then there was silence, and at the very end, it came back. That's why I asked. I wasn't sure if anything was happening.
Oh, okay. Sorry, I don't know sorry if it didn't come through all the way.
Yeah, we did hear it at the end.
Okay, great.
While I have your, could you? I'll ask a question. Help us differentiate the field of gravity as opposed to gravity waves.
The field
gravity is this attractive force, but how is that different from the gravity waves? Yeah, how is gravity different from gravity waves?
Yeah, so let me go back to this picture here. So just this analogy of this picture where you have a dip, right? If you have two of these dips next to each other, right? And they're sort of rotating around each other, then so you have one dip, that's gravity. That's the attraction, that a particle will fall into this hole. And that's just moving along what we say is a geodesic, but it's this particular path that the equations will just tell you this is the shortest path for this particle through time and space, and it will get pulled into this dip. If you have two of these dips, you're not seeing any sort of attraction or anything like that. You're actually just literally seeing, so the masses bend the space-time. Then some other mass comes by, and what happens to that mass is the force of gravity. So that is the force of gravity that we say in quotes as the force of gravity, because it's really just this particle moving through space-time. That actually is what's happening when the gravitational waves pass us. It's just that instead of it being some static thing, right, where now the particle will just move through, these are actually, this curvature, the way this is curved, is actually getting, it ripples out. I mean, just like this picture, where if the top of this pond is space, then as this thing moves by you, the space is actually oscillating. And we see that as this wave moves in this direction outward, things move apart and move back together. So, at a peak here, you would see two things moving further apart, and in the dip, you would see them moving closer together, let's say, if in the right direction.
I have a related question.
Mhm.
I think I'm missing something kind of basic.
Sure.
So if gravity moves at the speed of light, why are gravity waves not moving at the speed of light?
They do move at the speed of light.
Oh, but it comes out as 100 hertz, right?
Oh, but that's the frequency of this oscillation. So how fast are these peaks coming through at you? But that just means that you can calculate what the wavelength is from the right. It's the same equation, right? The speed of light equals wavelength times frequency.
So it's kind of like radio. It's like radio waves then, where it's moving at the speed of light, but the frequency changes. I got it.
Yep. It's basically exactly the same. And one of the things we try and do is measure the speed of gravitational waves to make sure that they really do move at the speed of light as has been predicted. Other questions before I move on? Hopefully I answered Ken's question. Some other plots and pictures later on might help with that as well. So this is just showing this oscillation, but really it's that, this waveform, this is what we're measuring. So this is like a 0. This is the trough of the wave. This is back to 0, and this is the peak of the wave. This is like a sine wave. That's what these sort of represent. This is like 0. This is pi over 2. This is pi, and this is 3 pi over 2. That kind of thing, where you're just looking at the wave as it goes through.
So if I can jump into the question on that. So unlike light waves, which can have any kind of polarization, you're saying you only get the 2 gravity waves, though, the 45 and.
It's the same as in, it's actually the same as light. So light can have any polarization. Any wave that's coming at us from space could be polarized in any particular way, but you can always decompose it into these two polarizations. Just like in light, you can just decompose it into two, whether it's 2 circular patterns or 2 linear polarizations.
Thank you, got it.
Mm-hmm. Okay, so this question I sort of alluded to about Einstein and not thinking he would be able to see these is this idea of how strong they are. And we measure this, the strength of gravitational waves in strain. So we're looking at some change in distance. So you measure the change in distance divided by the distance. This is the same strain as you would see in engineering when you're just trying to stress materials, things like that. We call it little h. And everything that has mass, any 2 moving objects that have mass, or a bunch of moving objects, give off gravitational waves. Anytime you have masses moving around, they do give off gravitational waves. It's just that unless the objects are very dense and very massive, it's way too small to see. So you can calculate what 2 human masses spinning. So this couple that's do-si-doing will have a strain of something like 10 to the minus 54. 2 battleships colliding will give off gravitational waves, and you get a factor of 8 increase, but that's still a pretty small number. in the end, the things we're going to be able to see are actually still pretty small, but Io, one of the moons of Jupiter orbiting Jupiter, is 10 to the minus 25. This is getting closer to what we can measure. A neutron star at the galactic center, a neutron star binary at the galactic center would be about 2 times 10 to the minus 19. This is something that LIGO can detect. This is right. This is too small, and this is in the this is something that LIGO can detect. And then the kind of things that I study are supermassive binary black holes at cosmological distances. We're talking about, you know, megaparsecs away, far away, obviously outside of our galaxy. And these are strains of like something like 10 to the minus 15. And these are things that pulsar timing arrays can measure. So, and I'll get to that in a second. So, but the question here is, I'm starting to talk about these black holes, and you know, there's this question, and just to kind of have everybody on the same page about what a black hole is. If I extended the analogy of earlier of the elastic sheet, basically, if you make the elastic sheet vertical in the bottom and you cut a hole in it, that's how people extend that analogy. We do not have that sort of analogy in Newtonian physics, but basically a black hole is a compact object with a really, really high escape velocity. Escape velocity is not the velocity a rocket would need to escape. It's the amount of velocity you would have to impart to a bullet to escape from some sort of gravitating body, right? So it doesn't get a rocket on a, you know, it doesn't have a rocket pushing it all the way out. It just has whatever you impart it with at the beginning, right? So if I shot a bullet in the air, how fast would the bullet have to go to be able to escape the Earth? That's right here, and it have to be going 11 kilometers per second, which is pretty dang fast. The sun is, you know, has this very, very high, it's a much bigger radius thing, but from the surface, you'd have to be going 618 kilometers per second. The gravity is much higher. So then you get to, so it can be the size of something, right? So the sun is really huge, but it's not actually that dense, at least compared to some other things. But something like a white dwarf, which is the remnant of a star, which is about the same size as the Earth, right? So these two are the same size, but the white dwarf is much more dense. It is some fraction of a solar mass. It can be, you know, anywhere from like 5% to 50% of a solar mass, but it's all shoved into something about the size of the Earth. And actually, the more massive it is, the smaller it is, because the gravity is so big it pulls itself smaller. And the escape velocity for something that this dense is much, much bigger. You can see that's 10 times bigger than the sun. It has, so again, the important thing is that it's not just the mass, it's actually the density that really matters. And in fact, there's things that you measure, you calculate for black holes called like where the event horizon is. And the event horizon is basically measuring a density. And it's where this, you know, how dense something has to be before it becomes a black hole. At the event horizon, that's the place where the black hole, where the escape velocity, that's what basically the horizon of a black hole is defined as, the spot where the escape velocity is the speed of light. So you have something that's just so dense that its escape velocity is the speed of light. Now, this was actually known in the 1700s. A preacher, a reverend in England named John Mitchell, actually brought a paper to the Royal Society when Newton was there and said he had predicted that if a star, and no one thought this would be true, but if a star could be made dense enough, then you could calculate this escape velocity that was the speed of light. Now, the interesting thing there is that no one knew that the speed of light was some sort of cosmic speed limit then, right? It wasn't until Einstein that we knew you couldn't go faster than the speed of light. So this was just sort of some back of the envelope calculation you could do that John Mitchell did. And everyone all thought, wow, that's a really nice piece of math, but useless as far as astronomy goes. And it's turned out to not be actually very useless, but very useful. Another analogy that you can think about here, again, imperfect analogy, but is imagine what the speed of sound is in water, right? There's some finite speed of sound in water. It's faster than it is in air, but it's still a finite number. It's slower than the speed of light. But imagine that you're this little fish and you've kind of come off of this waterfall, and this waterfall is moving very, very fast, much faster than a normal waterfall would move. And that there's some point when the water speed, there's some line where the water has accelerated so much that right here, the water is moving the same speed as the speed of sound is in the water. That means that this sound will never make it past this line because the sound can't move that fast. It can't actually move that fast. And so you don't actually, you can't hear this little fish crying for help on this side. Now you can't do this with a waterfall, but you can do this with nozzles. And so this testing has been done actually at University of British Columbia, where they make these nozzles that have very little turbulence and can shoot out water very, very cleanly. And then they, in the nozzle, in the downstream side, they inject sound and see what happens. And the sound equivalent of Hawking radiation, which is a prediction that Stephen Hawking made about this, some sort of radiation that happens, that's actually been detected, but in this regime when you're talking about water and sound, not with light and with black holes. But the theory actually holds there, which is really interesting. So again, sort of imperfect analogy with water, but that's the idea. Okay, so that's sort of a digression on black holes. I'm going to return to how we measure these gravitational waves. And I'm still going to talk a little bit about LIGO just because I think people are more familiar with it as I go to PTA. So how do you detect this motion? For ground-based detectors, we use interferometers, which basically is that you shoot a laser into a mirror, the light gets split between two mirrors and then comes back to a detector, and in that detector you measure the fringe, the interaction of these two beams of light, and that fringe tells you how these distances between this half mirror, this half silvered mirror, and these two hanging mirrors changes. So here's a little animation of that. The light comes back, goes to this detector here, and you get this interference pattern on this mirror that you're looking for. And that animation showed as a gravitational wave passed by. So here it is again, a little bit slower. The light beam gets split between the two. It gets reflected off the mirror, comes back to the half silvered mirror. Both of those beams of light come through, get combined, and move to this detector over here. And here they have it completely destructive interference, and then it moves as these distances to the mirrors change. This interferometric pattern changes, and here they're showing it again. So as that changes, as this gets brighter and dimmer, that tells you about the changes in distances to the mirrors and tells you about any gravitational waves that are moving by. Now, we have two of these detectors. There's one in Hanford in Eastern Washington, which I have had the pleasure of visiting, and then one in Louisiana in Livingston. And they're, they're 4 kilometer long arms with state-of-the-art optics. The people say that, some of the biggest quantum states set by perfect quantum states set by humans have been in these mirrors as they do some interesting quantum optics experiments to try and see if they can increase their sensitivity. And we have two of them because any sort of vibration that you get at one could just be something moving by. I remember when Livingston first opened up, they were actually detecting their seismic isolation wasn't so good, and they were actually detecting 18-wheelers that were driving by. Things like tumbleweeds can affect these arms. I've heard stories about crows making nests along here, and the tapping of the crows looks like some signal in the detector, and they have to go and scare the crows away to take care of it. So these are phenomenally sensitive instruments, you can drive to the end of these. This is from one of my trips there, and the mirrors are in these vacuum chambers. This is one of those vacuum chambers. This is my colleague Shane Larson, and just phenomenal engineering that's gone into these. And of course, they have successfully detected these gravitational waves. And so this is from the paper of the first signal, which the detection came in on September 14th, 2015. The two black holes that they saw were about 30 solar masses. And this, as you saw these theoretical predictions of what this chirp looks like, and you can see this is the data. And then this is the best fit model. This is 3 versions of the best fit model for what this data looks like. And then this is the noise that's sitting on top of it, right? So this is the signal minus, this is the actual data minus the signal, leaving you this much noise, which is very, very white. It looks like white noise that's left over. This is the signal from the Livingston detector. And this is the Hanford signal sort of shifted and moved to fit with this one. Now, because gravitational waves move at the speed of light, you expect these to be delayed by a little bit. And that's when we say it's shifted here. I believe that Hanford saw the signal a little bit before Livingston, and it's just a fraction of a second, tiny amount of time, whatever the light travel time is between these two, that is different between them. But you expect that to be the case, right? If they were too far apart or too close together or right on top of each other, then you know it wasn't a gravitational wave. And more recently was the detection of a neutron star binary, which is this phenomenal multi-messenger signal, where we saw in the gamma rays, so this is the Fermi satellite and the integral satellite, seeing this uptick in gamma ray count at the same time. The 2 detectors saw it at the same time, but delayed from the signal being seen in the LIGO Virgo detectors. And this is frequency versus time. So this shows you in the chirp, right? You have these longer wavelength things that go faster and faster as it chirps. And that's what we mean by chirping. It gets to be higher and higher frequency, and actually the amplitude increases a little bit. Gravitational waves move at the same speed as light, but they interact less with the interstitial stuff. So the stuff between us in this event, it does slow down. Even gamma rays that are very high frequency, high energy, they still get refracted or dispersed by the medium here, just by a tiny amount. But the gravitational waves don't really see those effects. So that's why they actually arrive a little bit sooner. So LIGO is still making phenomenal discoveries, but this one really opened the door to being able to see these with both light and with gravitational waves. There are other projects that are in the hopper. So the Laser Interferometric Space Antenna, which is known as LISA, is a project that has been green lighted by the European Space Agency. NASA is going to help with it. And it's 3 spacecraft that will shoot lasers between them. And these 3 paths act as actually basically 3 separate interferometric arms. Well, actually, this doesn't act as a interferometer, it acts as a Doppler ranging. So what you see is it's the same antenna, or sorry, it's the same laser frequency, but rather than looking at an interferometric pattern, you just look at a Doppler shift in the laser as the spacecraft move apart from each other because of a passing gravitational wave. And the LISA Pathfinder has been now out of commission for over a year, but it was sent up by ESA as a test mission to test some of the technology for this. And it was after this came back outperforming all of its goals. This is a picture of the inside of the LISA Pathfinder, which is basically like a mini LISA inside one spacecraft. There's these 2 test masses, and you're bouncing the lasers off of these test masses to see where they are and how they're moving. And all of that technology sort of passed with flying colors. And so this will fly in like 2034, 2035. Those arms are much longer, so this detector will be sensitive to longer wavelengths than what LISA is sensitive to. And I'll get into what it'll be able to see in a second. So I'll stop again and ask if there are any questions. I'm about to get to pulsar timing arrays, but all of that will help us understand what we're going to be doing with pulsars.
I have a question.
Please.
Could you go back 2 slides with the...
Sorry, you broke up there a little bit. This slide,
Go back 1 slide from here. Yes. Okay, you got Fermi, LIGO, and integral, and in each one you report the length of time after the detection, 16 seconds, 27 minutes, 66 minutes. I don't quite understand what the significance is of those detections occurring those time periods after detection. And
yeah.
also what was the detection against which these times are measured?
Sure. So the the actual signal, when you go back in and you do all of your data analysis, the time series looks like this. So that, this merger happened, they were counting the 0 by the gravitational wave observation, and then the gamma ray, these are gamma ray bursts that were seen by these two gamma ray detectors, and they were seen about, a little bit less than 2 seconds after the merger. So the merger happens and this gives off gamma rays. When these two neutron stars collide, they give off they're basically like two giant nuclei, and they give off a phenomenal array of heavy nuclei that decay fast, and they give off a big burst of gamma radiation. Actually, every kind of radiation, but gamma rays in particular, they're the first ones to arrive because they're the highest frequencies. That's just going back into the data and figuring out when everything actually occurred, just what the timestamps are. These times on the left are because these folks are very proud of how fast they got these alerts out to the rest of the community. So in fact, this neutron star coalescence was detected across the EM spectrum from radio to gamma rays, and everyone was looking for it, and they were trying to isolate it on the sky. These two spacecraft are all sky detectors, so they can sort of try and pinpoint where it's coming from the sky, but really they just see the gamma rays as they come in. They're not able to really pinpoint places on the sky very well. Gravitational wave detectors, because Virgo actually saw this, it was a little bit better, but still not very good, as opposed to like an optical telescope that can tell you something to within arc second capabilities. And the reason that these times are important is because these were reported, they were sent out as reports to the astronomy community that said, hey, we saw a gamma ray burst. Hey, we saw a binary neutron star coalescence. Everyone should be doing follow-up of this. And so LIGO is very proud that it only took them 27 minutes to do this. And these two, and Fermi only took 16 seconds to send that out. And Fermi's been up there for 10 years practicing how to do this. So that's a good question, because I didn't talk about this, but just from the astronomy community point of view, this was very, very impressive to get these alerts out, these bulletins out to the rest of the community.
We have another question. Yeah, go ahead.
Yeah, I'm wondering if there's two LIGO detectors, how do you vector like the source of where something's coming from if you only have two detectors and not three?
Good question. So when you only have two detectors, you can only you get a ring. The solution, as you're pointing out, right? You don't have enough information to pinpoint exactly where it is on the sky. So you have two detectors. They have sensitivity patterns, right? So the detector is sensitive, is not perfectly, like its sensitivity is not a sphere, right? It's more sensitive in some directions than in others. You can take that into account. There's this delay between the detectors. So even just using the delay between the detectors, you could sort of solve for a ring on the sky of where this is. And then that ring has an error bar around it because of your errors about when the arrival time was. Now you have two LIGO detectors and one Virgo detector. And so this was you could actually pinpoint this on to a blob on the sky that was still very big. By astronomy standards, very big, but you can, in theory, solve for this, although there's enough noise that this ends up being a pretty big patch on the sky when you have three detectors. Does that make sense?
Yeah, absolutely. So basically you can't really triangulate, but you can kind of narrow it down to a ring or a blob with a little more data.
Yeah, and then if you have even more detectors, the blob gets smaller. But the three allows you to triangulate, but with the noise, it's not very good in the sensitivity of the detectors. And the more you have, the smaller that gets. And then you just send out all of the other. I mean, with this event, the entire astronomy community, anyone who had hours, pointed their telescopes in that area, trying to find to pinpoint where this was.
So once Lisa is flying, does that act as a single detector in terms of the ability to triangulate, or because there are 3 satellites, will it help you triangulate?
It will help you. And in fact, there are 2 test masses in each satellite. And because there are 2 test masses, these 2 lasers, and these 2 lasers sort of in pairwise act as separate detectors. So you get 3 detectors, but because they're in the same plane, you're blind to some directions. Because they're not, if they were a little bit tilted off of each other, then you'd actually get a little bit more ability to pinpoint where things are in the sky. But you do take that into account because this is tumbling through the sky and the signals are long-lived. So if it was a signal like LIGO that only lasted for half a second, because they're in the plane, you wouldn't be able to tell exactly where something came from. But these are long-lived signals that stay in the band here for hours to days. And because of that, this is tumbling through space and changing its orientation. That actually allows you to kind of better pinpoint where things are going to be coming from on the sky.
How are they going to keep 3 separate things floating exactly the same distance from each other?
Yeah, they're not going to be the same distance from each other. They just have to keep the lasers pointed at each other. And again, this isn't a interferometer, so it's really measuring the Doppler shift from these things moving. So they're just keeping track of them moving. I will say though that the mission limit of this is the fuel it takes to keep these things pointed at each other.
Well, so if it's not, if they're not guaranteed to be the same distance from each other, do they have to know how far apart they are from each other when a measurement is taken?
No, because again, you can actually, for LIGO, the measurement is the change in length over the length, but you can actually keep track of what the velocity of the spacecraft are with each other, respective velocity. And so you watch the Doppler ranging, so you keep track of what the frequency of this laser light is doing. And so it as it vibrates, so when it goes, as a gravitational wave goes by, it will oscillate the spacecraft, and you'll see that as a change in the frequency of the laser. So you're keeping track of the actual frequency of the laser rather than the distances in this experiment. And
Okay.
as you rightly say, it would be impossible to do that in space.
Okay, so they just need to keep the lasers aimed at each other and they can be kind of wherever.
Yeah, exactly. But basically they try and keep them this equilateral triangle, and over time the equilateral triangle they'll get further and further from each other.
But if you were trying to calculate where the source was, would it matter how far apart they were when a measurement was taken?
No, because all the data that you look at really is just that frequency of the laser light, how that changes over time. It's not about.
Wouldn't you want to know so do you not get any vector information at all?
Oh, sorry, no, you're absolutely right. You know the full telemetry of the spacecraft, of where they are, within some error bars. I'm definitely not an expert on LISA, but they do keep track of these. They're very far apart from each other, but they do have radio telemetry on the spacecraft, pointed back at Earth, so we know where they are as they move through their orbit.
Sounds like I should get someone to speak on LISA. If you have any context, Jeff.
Yeah, definitely.
Talk about it later. All right. Go ahead.
Thanks.
Okay, so I will move on, and I just want to talk about, so the title of this talk is Searching for Lumbering Giants, and I'm going to talk about black holes mostly now, because this is what I've already talked a lot about black holes, but this is what PTAs are really, pulsar timing arrays are really sensitive to. It's been a really good few years for people interested in black holes. The binary black holes are this bread and butter signal for LIGO. There's this one neutron star merger that we have evidence of, but we've seen, and this is outdated, there are now like 40 mergers of black holes that LIGO has seen. And in fact, we've seen more black holes with LIGO now than we have with all of the EM black hole, the evidence for electromagnetic black holes that we have, which is pretty phenomenal, at least in the stellar mass regime. This is the stellar masses here on the left. So it's been really amazing. We didn't actually expect to see black holes, and don't let anyone from LIGO fool you. in the talks before LIGO turned down, the spokesperson and everyone, I'd go to these talks, and neutron stars were going to be the bread and butter signal. No one was expecting black holes this size. And the mechanism for making these is actually still not quite understood, and not out of my area of expertise, but it's an open question as to how do you get black holes this big, and people have come up with all different ways. Although now they've kind of tweaked their stellar evolution models to be able to make black holes that are that big. This past year, the Nobel Prize was given out for work on black holes. So Roger Penrose was given an award for basically proving that generically in general relativity that we get black holes. Basically, when you have mass and it gets very dense, you get black holes. You get singularities, and surrounded by an event horizon. So the mathematical proof of that. And then the other two laureates, Andrea Ghez, who is a phenomenal speaker, they got the prize for detecting and really monitoring the black hole at the center of the Milky Way galaxy. So there's this massive black hole at the center of the Milky Way. It's 4 million times the mass of the sun, but it's in a space that's basically they've shown that there's this thing that weighs 4 million solar masses, but it's inside something smaller than our solar system. And the only thing that we know of is that it's a black hole. And these folks all have phenomenal talks. They're really fun to go look up on YouTube. In addition to the sort of Nobel work is the Event Horizon Telescope. So if you haven't heard about this is another thing that would be awesome to have someone give a talk on. But basically, you can take a lot of radio telescopes and use special techniques with all of those radio telescopes to make the baseline of your telescope be the baseline between these radio telescopes, and look at phenomenally small areas that are far away and see. So this is the galaxy M87, and this is a silhouette of the black hole. This is the light that is passing around the black hole, and this light is coming from probably the accretion disk, this disk of really hot matter that's around the black hole, and this is coming from the other side. You can tell that the black hole is rotating in a particular way because the side that's rotating at you is brighter than the side that's rotating away from you. And they've calculated this to be 6.5 billion solar masses. So we knew that there's these, we call this a supermassive black hole. And we now know that, that these black holes exist, that they're massive. We've actually been able to see them. And this picture has even gotten better in the intervening years. They're now able to measure the polarization of the light, which gives them even better resolution on this, and seeing what this looks like. There's some neat general relativity that goes into the predictions of what this looks like, and there's a lot of signal processing that goes into these images from all of these telescopes. We now know, we now assume, astronomers, the community has seen that basically every galaxy that we can sort of resolve the center of, there's evidence for a huge black hole at the center of the galaxy. Whether the galaxies formed around the black holes or the black holes settled to the bottoms of the galaxies is an open question, but we know that most galaxies have them at their center. We also know that galaxies merge over cosmic time, which means that those massive black holes will end up in the middle. And so the question now is, the next thing we want to see is a supermassive binary black hole. So a black hole, one of the center of a galaxy that has two of these behemoths at its center. And so this is where, and this is even another picture. This is across the EM spectrum of M87, all of the different things you can see, the jets coming out of this active galactic nuclei. That's where this black hole, that's with this black hole at the center, which is the engine of all of this. So we're going to talk about pulsar timing arrays, and I'm motivating that by thinking about these supermassive binary black holes. This is the gravitational wave spectrum. So here's the wave period, and the wave frequency, right? So LIGO is up here in this regime, in the high frequency regime. LISA sees things in the middle, and PTAs, of which nanograv is one, sees things at the lower frequency end of things. And this is where the different detectors are sensitive. So what LIGO has really seen are these stellar mass compact binaries as they coalesce. Lisa will see them before they coalesce, like long before they actually get to the point where they coalesce, and so they're just sort of spiraling is what we say. Compact objects that have been captured by supermassive black holes, Lisa will be able to see, and they'll be able to see the mergers of supermassive black holes. That happens at higher frequencies. PTAs will be able to see these black holes as they are just rotating around each other. This is why I say lumbering giants. When I say lumbering, I mean nanohertz regime. So 1 nanohertz, 1/1 nanohertz is about 30 years. So we're looking at wavelengths that we're thinking about 10-year periods, 15-year periods. And that's the kind of thing that we're going to be looking at with PTAs. Okay, so pulsar timing arrays use millisecond pulsars, which are a special kind of neutron star. Neutron stars are the remnants of stars after they've gone supernova. Basically, when a star goes supernova, the inside, the core of the star is ash. We say ash, but really it's iron core. And the burning of the star is going on the outside. Well, when the supernova happens, the explosion goes out and it goes in. So the explosion actually implodes the star and collapses the center. If there's enough mass, it will collapse into a black hole. If there's not quite enough mass, it will get pushed into a neutron star. A neutron star is just a giant nucleus, right? There's more neutrons than there are protons, because it's the only way to have that be stable. But basically, the electrons get shoved into the protons. I am not a nuclear physicist, right? But this is basically what's happening. And you have this giant ball of neutrons. They're about 20 kilometers across, and the ones we're looking at are spinning thousands of times per second. The idea is that they are that the rotation axis is misaligned from their magnetic field axis, and they have phenomenally strong magnetic fields, and the magnetic fields accelerate particles and give off radiation along this axis. And what we see mostly is radio. That's what they're the most flux comes to us in the radio. And so you have this misalignment, and that's where you get the pulsar happening. These pulses come by every so often, depending on the neutron star and depending on the pulsar. It can be, every few seconds to a few thousand times per second. And these are very, very stable clocks. This graph here shows you what the period derivative is as compared to the period of the pulsar. And what's important is that millisecond pulsars actually all come down here. We're looking at periods that are real period derivatives that are very, very small. So they don't spin down very much anymore. And these pulsars have been formed, they've been spun up with a partner. They're in some binary system. And after they go supernova, you have a neutron star, it's spinning, it's doing its thing. And then eventually its partner starts to get bigger, because it's either a white dwarf or it's a big star that's just getting bigger. But as it gets bigger, the stuff that's getting bigger gets sucked up by the pulsar, and that actually spins it up, and it spins it up very, very fast, giving it a phenomenal amount of angular momentum and making them very, very stable clocks. And why the ticks of the clock are these pulses of radio light that we can see. And this pulsar 0437, we know its period to 15 significant figures. A phenomenal amount of precision that we know. And then we can predict its spin. We know its spin down as well, which is 5 significant figures smaller than this. So something like 10 to the minus 20 is the period derivative. So we can keep track of these pulses, and we actually keep track of every single pulse from these pulsars. The pulsar models keep track of every single pulse as we go. And pulsars have a really important history for gravitational waves, because this is the Hulse-Taylor binary system, which also won a Nobel Prize, because as a system gives off gravitational waves, it's losing energy. And as it loses energy, the binary gets smaller and smaller, because they get closer and closer, and they spin a little bit faster and faster as they fall into each other's orbit, because they're losing energy. And you can predict that using general relativity, and you can use pulsar timing to keep track of that. And so this is the line is the theoretical prediction, and these are these phenomenal data points from tracking this one particular binary pulsar system. And the error bars are really small. There are error bars there. And so this was a phenomenal, interestingly, a phenomenal observation that was done, and you can see over the course of 20 years here, showing that this system was giving off gravitational waves. Now, this isn't detecting gravitational waves, it's just showing that the power loss was from them. Pulsar timing arrays are really a galactic scale gravitational wave detector. On one end, you have the Earth, and we have our detectors of the pulsars, which are these huge radio telescopes. Unfortunately, the Arecibo radio telescope collapsed in December, but we still use the Green Bank. This is Nancy in France, and this is the Parkes radio telescope in Australia. And on the other end are our pulsars. This is just a sky map looking outward. These lines show you the galactic plane in this set of coordinates, and this is where all of our pulsars are. The code here just tells you whether it's an Arecibo pulsar or a Green Bank pulsar or a VLA. These are the three observatories we currently use for our data. And we are this, I'm going to skip that. That just compares pulsar timing arrays to interferometers. We can come back to that if people are interested. But we are searching for these lumbering giants. We're looking for these binary black hole systems. And this is just another flavor of the same picture I've showed you before. You have these huge systems, and there could be accretion disks around them, maybe some complicated physics happening, but at the center are these giant black holes giving off gravitational waves. And here in our galaxy, we're monitoring these pulsars to look for them. We look, what I'm about to say is true across the spectrum, but we look for three kinds of signal. A continuous wave signal, which is this sort of low to medium strength signal that you might see. It's a long-lived signal. You expect it to be there a long time. This is basically like a sine wave, continuous wave. That's what I mean, a sine or a cosine wave. This is a water example of one. There's very few frequencies, maybe only one, right? There's some frequency at which each wave crest lands on the beach. And here for us, it would just be as it passes through our detector. You also might look for a burst signal. Burst signals are strong to medium strength signals. They're short-lived. All of the compact binary coalescences the LIGO sees are burst signals. They have a lot of energy in them. LIGO was built on the premise that there's more energy right at that last half a second of these systems than there is prior to that, so you can really see the intensity of those systems. And they have, there's many frequencies used to build up these signals for these burst signals, because the frequency is sort of changing as you get to that point. And then there's one last kind of signal that we look for. And for PTAs, this is going to be the most important one. So this is kind of another reason I'm building up here. And that we call that a stochastic background. Sorry. And a stochastic background is a sum of a bunch of signals that you can't see by themselves. Basically, everything is so, all the individual sources are so weak, you can't see anyone individually, but you can see all of them added together. It's also long-lived, it's many frequencies, it often follows some sort of functional dependence in frequency space. So the power in gravitational waves, there's more power at the lower frequencies than there are at the high frequencies. This is this wonderful painting by Gerhard Manz, where you see you're out in the ocean, and instead of seeing something like this or like this, you see the addition of all of the waves and all of the directions. And there's big low frequency rollers and really high frequency waves on top of that as well. And so we're in pulsar timing arrays, we can look for all of those, but this is the first signal we expect to see, is this stochastic signal. I'm going to attack that from a different standpoint here. And so another way of thinking about the stochastic background is, again, to just build up all of those single sources. So I have an animation here on the left, and let me describe to you what's going on before I start it. Every point on the sky here shows you what the gravitational wave strain would be from that source if there was a pulsar there. So if there's a pulsar here or here or here, the strain is dictated by by the color here. So the dark purple is positive, the white is negative, and these lightish blue tones are like 0, right? So this is the crest, this is the trough. And this hourglass shape here is the pattern that you get from a single source. As it sweeps across this pulsar, you'll see it crest and then go trough and then crest again. And as it sweeps across the orange, you'll see it reach its crest at a different time. and likewise this blue. So these 3 stars are what the time series of the strain would look like. And you can see that, again, this is over years. So I'll start this. This is one single source right in the center. And hopefully you can see this sort of spinning hourglass shape. This is a sinusoidal signal, circular binary just spinning around itself. I'm going to put a different source here at a different part of the sky. It'll be up here on the right. Here it is. It's very similar, but now it's a different part of the sky. So what you see in the pulsars is different, right? You're far away from this orange source, so the amplitude is much smaller than it is in, say, this red or this blue pulsar. So you expect it to be smaller here and bigger here. Here's the addition of both of those. This is a much smaller source. So mostly you see the sinusoid from this big source that's at the center, but you can see already I've sort of lost the sinusoid shape. So I'm adding these together in time. Here's the third source that's sort of on the edge. Now the yellow is the closest pulsar on the sky to it. So you really see the strain in this pulsar stronger than you see it in the other pulsars. And now I'm going to put all 3 on at one time. And again, these traces sort of start to lose the sinusoids, but you can see some sort of pattern as over time as you keep track of this. Now, the next version is going to have 200 sources added together. Okay, so this is the 200 sources added together, and you've sort of lost that single source here and here. You can maybe see some evidence for them a little bit, but really you're seeing these sort of patches of purple and white move in and out on the sky. I'm going to show it here again. And when you look at the traces down below, now you've lost the sinusoidal pattern altogether. But if you decompose this and you look at the power that this signal has in all of the different frequency bins, then it will follow a power law. It will follow something like this. So some amplitude, and then the frequency depends on what frequency you're at. And this negative sign means there's much more power, there's much more strain at the lowest frequencies than there is at the highest frequencies as you go. So you can see that just by looking at this, right? That you don't really see a lot of really small frequency stuff here. You see this really low frequency power.
I have a question, Jeff. I'll come back to the word strain, which you've used on and off through this thing. So I guess at this point, I sort of need to understand exactly what you mean by strain. Is that, well, what is it that you mean?
Yeah, totally.
Is that how that is straining the gravity, or
so the strain is the thing we measure. And in an interferometer, I'm just going to come back to this slide because I have both of them here. In an interferometer, you measure the change in length, but you actually measure it as the change in length over length. So the strain is this dimensionless quantity that's telling you basically what fraction of the length between, in LIGO, what fraction of the length between my mirrors did I see this change? So the mass has moved a little bit. What fraction of the total length did they move? For both for LISA and for pulsar timing arrays, right? In pulsars, it's the frequency and the period of these things that is so accurate. So what we actually monitor is the changes in the period of the pulses. And I actually think I glossed over this. So we really are monitoring the frequency at which these pulsars are pulsing at us. And intrinsically, there's some spin that we expect from the pulsar, and we actually monitor that the spin, the frequency that pulse comes at us changes over time. And so the strain that we measure is actually, we look for this change in frequency of the pulses. And it's the change in frequency over what the sort of fiducial frequency of the pulsar is. That's the strain that we measure for those.
Okay, I think I got an idea of that. I'm curious how it got the name strain. There must be some
it's the
etymology there.
Yeah, the etymology is actually from engineering. So the strain on a block is if I push on a block or I pull on a block, how much force, there's all of these sort of things that you learn about. So if I take like a 2x4 and I pull it, how much, if I pull it with so much force, it will change its length by so much. And that strain just tells you about the strength of the 2x4. So there's compression strain and tensile strain. And it's always measured in the change in length over length. And so it's just this old word from engineering that it's the same quantity. So we use it in gravitational waves.
Got it. Thank you.
Yep. But good question. Any more questions that anyone has before I move on?
Yeah, kind of one quick one. So you were talking about the different number of sources, one source, two sources, but when you have when you're sensing, when you've got sensors set up around the world or whatever, don't you have a really large number of gravitational sources to sort out?
Yes, we do. And in fact, that's in some sense, that's what this kind of picture is, and that's what this animation is showing, is that we really have, we're going to be looking actually at that there'll be thousands of sources in the sky, and we have to pull apart all of those sources. But really what we end up measuring is sort of this conglomerate thing, which is the power that we have in the power in gravitational waves at different frequencies. And so we can't necessarily, there could be many binaries, and I wish I could skip ahead in this, but I won't be able to. But there's many binaries in a frequency bin, and they all add up to have some amount of power in that frequency bin. And in the end, a lot of the time, this initial signal that we expect to see, at least, we will just be measuring how much power is at a particular frequency.
So
And we know it's gravitational wave power by some filters that we can put on it.
do you just do like an enormous number of Fourier transforms?
Effectively, although all of our analyses are done in the time domain, because we can't we can't do Fourier transforms easily because we don't have evenly spaced data, although we know there are techniques to get around that. But yes, basically we're doing a slightly more difficult Fourier transform to look at what the power is. And I will get to one picture where I'll show you a measurement of the power in all of the frequency bins. And we're monitoring pulsars here. There's 3, but we're monitoring 70 over the whole sky that we look at. I'm going to go through these quickly just so I can get to some of the more astrophysicsy things. But one of the way that we look for the signal is by correlating the data, and we expect there to be a specific correlation in the data streams from these pulsars and the change in strain from these pulsars over time that's dependent on where they are on the sky. So this is my toy PTA here. There's these 3 pulsars on the sky, and we expect their data to follow a correlation that is dependent on how far apart they are. So the circle and the star are about 20 degrees apart from each other on the sky. The correlation factor, and this correlation is basically just an integral over the data. You effectively multiply the data in a fancy way and take the integral over it, and you normalize it and get a number. And that number tells you about how they're correlated. And that should depend on where they are in the sky with relative to each other. And so they should fall on this curve. This is called the Hellings and Downs curve, predicted by Hellings and Downs in the 70s, or yeah, in 83 actually, sorry. And it's these spatial correlations that are really the smoking gun signal for gravitational waves. So not only do we have to look for the power, but we have to look for these spatial correlations. So we do this is a cartoon version of it, but we're basically looking at the correlation matrix for all of these. So this along the diagonal would be the data for one single pulsar, and then we expect the cross correlated data, so between this circle and star pulsar, to have, when we do this integral and this normalization, we expect it to have some number associated with it, this correlation. And you can calculate those, and correlating the real data is messier than something like this that just falls perfectly on the line. But here's an animation of where you add pulsars to this array, and as I add pulsars, I get dots of where this is correlated. This is more realistic data, and it has noise injected into it. So this is my sky map of where the pulsars are. This is how many pairs I have in a given bin, of angular separation. And this is what it really looks like. The correlations are sort of all over the place. But if I take a bin and I average them and I average the error bars, then I start to get something that follows this curve. So it's a kind of real messy, this is in the end here, we'll have like 30 or 40 pulsars, 45 pulsars, I think. And that will give us many pairs. So it's n minus n times n minus 1 over 2 pairs. And I get a bunch of correlations for that data. And this is what it really looks like. If I do some averaging over bin sizes, then I get correlations that start to follow this theoretical curve that I'm expecting. And this data processing is what I do. This is the part of this that I'm very heavily involved with, using Bayesian data modeling techniques to get to this point. So that's why I'm sort of digging in a little bit here. And it's a weird problem, because it's not just like we're not looking for a signal with a template like in LIGO. We're looking for this sort of statistical correlation between the pulsar data streams that tells us about what part of the signal is gravitational wave.
And so what you're looking for is a correlation between these pulsars because of the gravity waves traveling between them.
Exactly.
Or a bit because of gravity waves hitting each other or something.
So right. So the part that's correlated, right. So as the gravitational waves move through the galaxy, right? So our detector is really our half of the galaxy. The arms of our detector are the pulsars that are 1 to 8 kiloparsecs away from us. And as the gravitational wave passes through the galaxy, it imparts this motion, right? But it's not just one gravitational wave, it's many from different directions. But it turns out that theoretically, this blue line is predicted as there's this correlation that's predicted because those correlations are formed by gravitational waves. You can show that they should be correlated according to their angular separation by this curve. So what you said is right. I just said it again, I think. But
who came up with this concept?
So this is called the Hellings and Downs curve. So Ron Hellings was a faculty at Montana State, and yeah, this idea of using pulsars was really, really hot in the 80s, because in the 70s it won a Nobel Prize. Well, they knew it was going to win a Nobel Prize in the 70s. I think it didn't win until 80 something. And so the use of pulsars to do these kind of measurements was really, people were investigating various things you could do with pulsars because they're such precise clocks. And this just happened to be something that someone came up with because at the time, we still were far, far away from building a detector. We didn't even start the LIGO detector for another 25 years, 20 years after this paper came out. So, so people were trying to come up with ways, and in some ways, right, this is a lot cheaper because people at the time thought maybe you could only, you only needed like 10 pulsars. We now know we need a lot more pulsars. And it also depends on how strong the gravitational waves were. The gravitational waves weren't as strong as some people had predicted, so it's taken us a little bit longer to see them. But that actually tells us something about the universe too. So
that sort of gives me an opening for a question that came in from Ted here. Are there practical applications of this science? And he uses an example that made the news recently, that the US Navy lab recently filed patents about the propulsion by means of altering space-time, which many people consider,
yeah,
woo-woo science. But is there anything other than just age of the universe or other, pure science? Is this pure science, or are there applications, I think is what
sure.
Ted is asking.
So we use this, we're going to use this to tell us about the population of supermassive binary black holes. That's one thing. I'll start with the astrophysics a little bit. I'm going to go on to that in the next couple slides, depending on how much time we have and how interested people are. But this can tell us a lot about merger histories of galaxies and how galaxies have formed and how many black holes we have at the centers of galaxies, that kind of astrophysics question. We can also do like tests of gravity and try and understand, whether general relativity is the correct theory of gravity. And then there's also predictions for gravitational waves from things that happened at the Big Bang and other like particle physics predictions. We can even look for something that has nothing to do with gravitational waves, but it's another interaction that has to do with dark matter. And so those are questions that we can answer now. I don't think that that's really necessarily practical. But I will say that the data analysis that goes into this, I have friends who did their PhD in LISA and LIGO and PTA data analysis who can't tell me what they do, because It turns out when you're looking for a really weak signal in very noisy data, that the NSA would love to talk to you if you're an expert on that. So while the full-blown data analysis package that we're using for gravitational waves isn't applicable to the everyday person, the signal processing techniques are very, very useful, and we're sort of at the cutting edge. The beginning, LIGO learned from the cell phone industry, and then now it's sort of going back the other way. So
that's particularly interesting to me because I do some of that signal processing in my application that I work on. And what I use came from the cell phone industry. Now I have to look and see whether you guys got something that can take me a step further.
Awesome.
That's an aside.
Yeah.
Thank you.
One other thing to add to that is LIGO has actually pushed optics quite a bit. I remember the very first American Physical Society meeting I went to after they announced the detection. There was a like a banquet put on by the American Optics Society, because they've gotten phenomenal, like just coatings science, the power that's in those lasers is very, very strong, and it strips the coating on the mirrors. And so they've had to like push the like technology for putting coatings on optics and making these mirrors be as perfectly, I don't think they're spherical mirrors, but whatever shape they are is perfectly whatever is possible. So there's also the sort of optics technology as well. So
Well, that's actually shouldn't be downplayed, that some of this pure science does have spin-offs that are practical, and you just never know what they're going to be until it happens.
yeah, absolutely. I'll go through these next few slides. I only have a few more. I know ostensibly, well, let me just ask actually, Ken, what would you like me to do? I can talk for maybe 6 more slides, or we can just talk more generally about what I've shown so far. I'm happy to do whatever anybody would like.
We can, if anyone in the audience has suggestions, please speak up. I'd like to hear more about why this is taking so long. You talked about this being a very long-term project, and exactly where you're getting your data from, I guess these radio telescopes. So I'd say just go through the slides. We can talk, we've got a full half hour left if people stick around that long. So unless there are specific questions, I'd say just continue.
Okay, great.
Question from Mike.
I have a question.
Please.
This is a general question, and you could answer it at the end after you've shown the rest of your slides. That'd be fine with me. But you've shown us quite a few different projects, each one of which is looking at a different part of the spectrum or using a different technique to look at some aspect of this same overall program. Some of these projects look extremely expensive, others less so. And I'm curious as to what the cost has been. I know LIGO, for example, was a very expensive is a very expensive project, but I'd really be curious to see how these compare in terms of cost efficiency and whether you think one or another approach has gotten more bang for the buck. Again, when it's convenient for you to address if you wish to.
Sure. I can answer right now that probably LIGO will be the most expensive. I'll first say that I know how much money has gone into Nanograv specifically, and I can only speak in generalities for the other ones, so not very specifically. LISA has a limited mission life. It ostensibly will hopefully make it to 10 years, 5 years, and then 10 years. And obviously a space mission is very expensive. But over its lifetime, it will be less than LIGO. So the ground-based detectors do cost more, and they've been being built since the mid-90s. And the folks who won the Nobel Prize for that, part of the reason that they won the Nobel Prize, they really put their phenomenal careers on the line very early on to sort of say that they would be able to actually see these gravitational waves. And it took 20 years for LIGO to start building. And they knew right along the way that every time they would turn the detector on, people would expect them to see something. And they knew when they would see it. And literally when they turned on the observing run 01, they saw something. And then science run 5, which was the last run before that, they didn't see something. they're always getting science out because they're always setting limits on what they could see. But you know, it's a hard environment to be in to have a detector that's 20s that is 20 years old and you haven't seen anything. That's and they finally did see something, and now they're seeing tons of stuff. But they were building a completely different way to see the universe. So it's definitely will be in the in the hundreds of billions by the time its lifetime is over with. On the other hand, PTAs are much cheaper. I said billions. I didn't mean billions. I have hundreds of millions of dollars. PTAs are we've gotten in Nanograv from the NSF about $30 million, which is a lot less than either of the other two missions. And part of the reason for that is that, our detector, half of our detector is an astrophysical system, and the other part is these radio telescopes that were already built, and it can be used for other things and have already been used for very good science. At Arecibo, Arecibo, it collapsed, but we got all the money. We squeezed a lot of science out of it for the money since the 60s. And these other places now, Nanograv is actually getting like a quarter of the time at the Green Bank telescope to monitor these pulsars. And we're paying for some of that from NSF money. We're paying for some of it from private funds actually as well. Breakthrough Listen is this big project that gives out money to these types of pure science things. So that's about as much as I know, but I would say we are definitely, even though we're a longer term project, a good deal cheaper because we didn't have to build any technology. We just used the radio telescopes we have. And that technology can be used for other things. Our bread and butter signal is supposed to be these binary black holes. And there's lots of questions that people ask about them. I love this plot over here because there's a bunch of black hole masses, and the masses are plotted against the bulge size of the galaxy. So there's these relationships between black holes and their galaxies. And it's just this scatter plot, and these 4 different groups have 4 different lines they put through here. And we're trying, and one thing is that PTAs will be able to kind of pin this number down a little bit better and tell us that the size of a galaxy and the size of the black hole are actually related in some way. And that will also lead to telling us about how many galaxies have black holes, how many big black holes are there, how many galaxies have gone through multiple mergers in their lifetimes, things like that about the history of of galaxy mergers and evolution. We do directed searches at some of these quasars, which are these active galactic nuclei, that basically galaxies with very, very bright cores that are driven by black holes. We know there's at least one black hole there. Some of them show periodicity in their light curves that could lead to them actually maybe being a binary black hole. So we can do directed searches at them and sort of see if we search to this one particular point in the sky and make our parameter space a little bit smaller, can we set limits on what the masses of those are. We do more targeted. We've extended that to targeted searches across galaxies that are really close to us. So this is, well, close by galaxy standards. So within 500 milliparsecs, this project has sort of set limits on what the masses can be given our data stream. We talk about and think about what the physics at the centers of these galaxies are. If there's 2 black holes, do they each have these accretion disks? Is there another in simulations, you see that there's a accretion disk outside of the black holes with smaller accretion disks inside? How does that change? How does that change what you expect from the EM signature? How does that change what the binaries would look like? So there's all of these questions you can ask. You get into more esoteric questions. So I mentioned that there's these 2 polarizations predicted by general relativity. There are 4 more you can have if the theory is this type of theory called a metric theory, which is general relativity is the simplest kind of metric theory. You can make it more complicated and come up with a number of wild predictions for these theories. Now, you could say, well, what would be the motivation for these types of theories? Well, some of these theories can explain dark matter, dark energy, and so you see if they predict the same types of gravitational waves, and then see if you can detect those other modes, the other polarizations. That's one type of thing. Cosmic strings are this thing, this crazy thing that is predicted by both string theorists and by particle physicists. Particle physicists basically predict them as like defects that happen in space-time when inflation happens at the Big Bang. You just have basically the universe is expanding so quickly it causes these slight defects, and those defects ring as they sort of ring off their energy and give off gravitational waves. And you can look for the signature of those gravitational waves. It looks different than the one from binary black holes. You can look for dark matter, this type of particular kind of dark matter called fuzzy dark matter. And this is not gravitational waves. It's actually an oscillating gravitational potential, a Newtonian potential that you look for in the galaxy. So you're seeing if there's dark matter in our galaxy, and that affects the arrival time of our pulsars from the radio pulses. So we can search for that signal as well. So there's all of these things we can do. So sort of any signal that's in this band, we've built a detector, right? LIGO has built a detector. Lisa is going to build a detector. It's a detector that is sensitive to anything in that frequency band. And so any signal that someone can come up with, we can set limits on it or see it if it exists. Right now, we really only expect to see the supermassive binary black holes because we know that black holes exist, right? The sort of astrophysical prior on that source is much better than other ones. This is the promised picture I was going to show you of the power and the frequency bands. This is our most recent results, and I can go into more details here, but the gray blobs I think are the most interesting. The blobs just show how much power we have at different frequencies. This is our 12.5-year data. So this is the time span. This is 1/12 years. And this answers the question, Ken, of why it's taken so long. So if I look at this system here, these little blobs are, they're Bayesian posteriors. So they just are telling you the probability that there's power at that given measurement. This is in residual. This is a particular thing that basically this is a square root of power. That's the best way to look at this. And in a lot of these are upper limits. This is called the violin plot. If the violin plot goes all the way to the bottom, it means that we really don't have a very good detection. We just have that there's some upper limit. We know that there's power below here. If there's any power, it's below here somewhere. And this blue line sort of shows our baseline noise, right? And so at higher frequencies, and all the way really across the band, we have this noise. And the power we expect to see from the background looks like this orange power law. These orange dashed line is what the power we expect to see. Not very much at high frequencies, like I said. Remember back to the plots, the picture I showed of strain. There's not in the plots in the bottom as you saw the strain versus time. Big, low frequencies, you expect to see lots of power, not a lot of power at the high frequencies. Our noise level is somewhere in here, and it's not until we have 12.5 years of data that we become sensitive to the power in those lowest frequency, that we start to see power because it's finally at these lowest frequency bins starting to peak above our noise floor. And so that's why it takes a really long time for this. And right now, really, we only have 2 significant data points. So we're fitting a line to these 2 significant data points. And this over here, this blue and orange dashed lines, that's fitting the amplitude and slope of this blue and dashed orange line here. And you can see it's pretty big error bars, or pretty big posterior, these contours over here. And so we're just fitting it to those 2 data points. Now, as we get more and more data, we expect to get more significant frequencies. The more time span we look for, not only do we get more power at low frequencies, we also get more sensitive. The bin size gets better as well. This is like the Nyquist limit for just how long we've been observing for, basically. And then I just wanted to show this picture because this is our current state of our spatial correlations. And I like to show this because, this was the best fit Hellings and Downs curve, like I was talking about before. And this orange line is the best fit monopole, which just means all of the pulsars have exactly the same correlation. And you can see that we're still not in the case where we've actually detected the gravitational waves. We're still waiting because the straight line fits basically as well as the blue line. But we hope, and we're starting to see hints of this, right? That we have negative correlations here, positive correlations here. We're starting to see hints of that, that these, these error bars will get smaller and smaller and start to follow this blue dash line. That's my.
So could you, if you had more antennas, would you be able to collect more data, or there's only so much data coming in no matter how many detectors you have?
The more telescope time we have, the better. And we can use it in two different ways. We can either look at the same pulsar for longer, and that actually helps us with the higher frequency sensitivity, or we can look at many different pulsars, but for not as often. And that helps us with the lower frequency sensitivity. And so the more time, the more telescope time we have, the better. And in fact, Nanograv is just one of a few pulsar timing arrays around the world. And together we make up something called the International Pulsar Timing Array. We put all of our data together. We monitor some of the same pulsars, but some of different ones. Like Parkes is in Australia. They look at different pulsars. They can see a different part of the sky. So we add all that data together, and we actually have a much more sensitive detector when we put all that data together. And the more, the better. There's projects that are in the works, something called the Square Kilometer Array, that if we could start seeing pulsars with that, we would we'd get a lot more lines of sight. The more lines of sight we have to different pulsars, the more time we have on those lines of sight, the more sensitive we are.
Yeah, I just put a link to the International Pulsar Timing Array in the chat group for people who want to follow up on that. How long have you been involved with this, and what was it like for people who've been involved, say from the beginning, knowing that this is going to be a 10, 20, 15, 20 year project? Again, like the LIGO folks.
It's a good question. So this is my last slide. It's just a picture of some of us. This is from a meeting at the Green Bank Telescope. There it is in the background in the rolling, beautiful hills of West Virginia. Yeah, I have not been in it from the beginning. I was a very deep theoretical gravitational person in my PhD, and started moving towards data analysis and astrophysics observations in my postdocs. But I've been in the project for 5 years, and it's interesting because 5 years ago we weren't quite sure when we were going to see anything. Now we're starting to get hints that in the next data set, or the one after that, we'll probably detect the background. We're starting to see hints of it even in this. Like I said, these blobs are really, they might not look like much to you, but to me they mean a lot. And as we get more of them, we're going to really start to see very strong statistical significance for the signal. It's been really interesting talking to people who've been in it from the beginning. In the beginning, people thought they were going to see the signal right away, like right away being in like 5 years. And that was because the modeling that was done and the predictions for how many of these supermassive black holes there were actually just more optimistic than nature had intended. It's similar to LIGO, where they thought they were going to see lots and lots of neutron stars, and they haven't. And none of them thought they were going to see black hole binaries, very many black hole binaries, but that's mostly what they see. So sometimes you just get lucky. PTAs, for a while, there were people, you hear about this back in the heyday, where there were people predicting that they would see gravitational waves before LIGO would. So there are definitely people who sort of bet bottles of whiskey that they would detect gravitational waves with their LIGO compatriots. And then I think there was a generation after that who just didn't know how long it was going to be, and knew it would be a long haul, and that there was a lot of interesting work to do on the data analysis aspect, and sort of what you could do if you could start to detect these signals. I kind of came in right at a perfect time, where I had a few years of thinking I didn't know how long it was going to be, and now I know that soon we're going to see something, or we're not going to see something, and then we'll know. But once we start to see something, it's going to get really interesting.
Do you ever find it like terrifying or depressing that apparently the universe is made of these massive blobs of mass that are just slowly all merging with each other?
It's a little depressing. There's a really good book called The End of Everything, written by a cosmologist recently, Katie, what's her last name? It's a really good book. And
Well, I know there was an Italo Calvino book that was about the Big Bang told from the perspective of all of the matter being lonely because now they're so spread apart and
oh,
they used to all be, together.
that's hilarious.
Yeah.
That sounds like Calvino, all right. Yeah.
It's just gonna get farther and farther apart for sure, and everything is going to coalesce into black holes, and then they will all evaporate from Hawking radiation, and that will be the end of it. But that's a long ways away, so it's not that depressing.
Great. Jeff, this is great. I want to open it up for any last questions here. You've been talking for a long time. I've personally found this absolutely fascinating. I hope other people have too. But we should let Jeff go here. Jeff, can you give me a copy of the slides or post somewhere where I can post the link when I post the recording of the show?
Yeah, I can do that.
Okay. Yeah, you can either send to me and I'll put them up somewhere, or you can post them and send me a link.
Okay.
Whichever is easiest for you. Yeah, great. Any other questions out there?
The whole terrifying thing was my last big question, but this is the closest I've come to feeling like I understand astrophysics. So I just thank you for taking the time to go through this. I'm an engineer. I do some radio stuff, and I think this really helped me kind of map it back into my own frame of reference.
Awesome.
And I feel like I actually have my head around kind of there's a bunch of data processing, but I understand what the data sources are, the sensors, and I don't know. I feel like I learned a lot. Actually, I do have one question. I was kind of wondering, when you were playing those audio files of binary black holes, do you have those in wave format, or are those on the internet somewhere?
You can definitely search for them. Those a LIGO colleague gave those to me, but LIGO has now posted many versions of them. So if you just search for something like, LIGO sound wave, I don't have them in wave. Those were in QuickTime format because that's just what works for this PDF format that I'm using. But
Yeah, right on.
Can you talk maybe briefly about your group and Jerry Key's group? How big are you guys, and is your focus on astrophysics or cosmology or cosmetology or or gravity waves in particular? Or
yeah, so Joey works in LIGO, LISA, and Nanograv and PTAs, and she has her whole career. She started in LISA actually with LISA work, but it's all very similar, right? It's all some sort of and she does data analysis. So our team is really data analysis. To sort of diehard Bayesian statisticians, figuring out how the code, doing the coding for getting the models to work and the sampling to work for the Bayesian analyses, and that's really what the focus is of the group. I work particularly with PTAs. I'm sort of starting to learn about LISA, although it's a huge envelope of stuff to learn about there. She has students who are working on all three detectors though.
So if you meet a young person who's looking at data analysis of physics, UW Bothell is a really good place to go.
Yeah, definitely.
Yeah, heavy that kind of, I don't know what do you call that kind of math?
Well, some people call it astrostatistics. But I mean, I mean, we mostly say we're data analysts,
Yeah.
or signal analysts, signal processors, I guess. I don't know.
Okay. On that note, unless there are any last minute questions, I want to thank you very much, Jeff, and I'll give my regards to Joey as well. This is fantastic. I will get the recording up in the next couple of days onto YouTube and give you a link before I make it public so you can review it if you wish. I'll have to edit myself out. And anyway, thank you all. Thank you all for attending, and Jeff, thanks again very much. This is fantastic.
Absolutely.
Really.
Thanks all for inviting me. I appreciate it.
All right. Good to see you, Mike, too. And you I'll be in touch with.
All right, have a good night.
Good night. Thanks, everybody. Over and out. let's see.